Hey, welcome back. I'm Pat, and this is my devlog on exploring a variety of topics in game development in preparation for my computer science capstone coming up in the fall. Since we're just starting out, we're going to need a character controller. In the spectrum of character controllers, we have animation-driven controllers on one side. If you're going for a more realistic approach, these are better suited, as the animation artist gets as much control over the experience as possible. On the other side, you have procedural-driven, where the character uses math and algorithms to decide how to move in their environment. Since I like math, I'm gonna be heavily leaning on the procedural approach. Another plus is that I find this approach way nicer to iterate on, as you're not bouncing between Unity and your animation software, like Blender. After setting up my development environment, I got caught up to speed on the new Unity input system, as I was only familiar with the old one. One quick little tip, if I'm ever having to work with strings, I avoid rewriting them as much as possible, as I'm pretty bad with making typos. Since we've got to pass in a string to the input system for getting actions to read, I like to have an in-between class where I define all my actions as variables. We start our character controller by adding a rigid body component. With rigid body controllers, we've got to make sure we're not directly modifying the rigid body's position field. This is the same as teleporting our character around. So if we teleport into another rigid body, we're going to get some weird behavior. There's also a move position function, but this automatically interpolates the movement over a period of time. Instead, we'll be calculating and controlling the linear velocity field of the rigid body every fixed time step. The downside here is that manually changing this can lead to non-realistic physics, but that's alright with me. If our velocity is directed into a wall, the physics engine will stop our position change right before we clip into the wall, which is what I want. With that, we've got our planar XZ movement. This isn't too exciting, and it may even feel slow. If we just crank up our velocity, things look fast, but controller-wise, it feels very slippery. If the player needs precise control, this is going to get frustrating very quickly. The core of this issue is that we don't have a visual sense of speed to begin with. Now, before we start talking about procedural animations, let's talk about some system architecture first. Let's imagine we have 3 or 4 effects going on at the same time. It's very reasonable to assume that our script file is going to get very bloated, with each effect having a variable to tweak in the inspector. Our inspector is also going to get bloated. Since everything is together, each time we want to add a new effect is going to take longer and longer to develop, because we're trying not to break everything else in the process. The solution I came up with is to have an array of components that I arrange in the inspector. Each of these components inherits from a programming interface. Think of these as blueprints that require a function to be declared. If a class implements this blueprint, we know that it has this particular function. The only downside of this approach are on the Unity side. As far as I know, we can't have an array of interface-typed objects show up in the inspector. So we've got to use an array of components and do a type check. The other downside is that I need to open up a second inspector to drag in the particular component to the array. Oh well. Anyways, back to procedural animation. With a rapid fire, we've got the character facing the direction of their velocity. A foot fart particle system where their start size is based on the velocity's magnitude, leaning back opposite to their velocity, and then adding a sine wave to get a nice bobble effect. An arm swing animation also based on their velocity's magnitude. And finally, and most important of all, eye blinking, because I just think it's fun. Plus that it shows that our controller doesn't have to be in direct control of our effects all at the same time. I'll expand more of this in a bit. Putting all of these together, our sense of speed is a lot more defined, I think it looks nicer, and it feels better as well. Now, before we add vertical movement, we've got to know when we're on the ground. We'll do this with a short sphere cast downwards to check if a collider exists with its layer set to walkable. Rather than doing a ray cast, a sphere cast will give the player a lot more wiggle room. This is also more noticeable when the player is on a ledge. Rather than going for a purely mathematical approach, we're going to design off of feel. We'll define a set time for the ascent duration, we'll also have a base vertical velocity, and use an animation curve to taper off that velocity as the ascent time gets closer to its limit. Once the ascent time has passed, we'll begin applying a downward acceleration due to gravity after each frame. An important thing to note that I didn't mention earlier is that fixed update isn't called every frame.
There is a very real chance that our input is straight up ignored if we're listening for a key to start being pressed on a frame. To solve this, we'll listen for inputs in update and let the next fixed update know of the request. For jumping, we have a jump requested boolean that update sets to true on input, while fixed update processes that request and then sets the boolean to false. Now let's get back to some more fun stuff with procedural animations. We have squash and stretch depending on the sign and the magnitude of the vertical velocity. As an animation principle, we want to conserve our mass. As we squish our character, we should scale the y-axis while scaling up the xz axis. When we stretch our character, we should scale up the y-axis while scaling down the xz axis. We'll have even more foot farts happen when you're jumping. And finally, and most important of all, we have eye blinking when the jump starts. With that script, our apply animation method resets the blink timer that update acts on. Back to some features that interact with controls, let's implement coyote time. This is a common feature in games, often hidden, where even though the player has fallen off a ledge, they can still jump. Luckily, the implementation is as simple as a timer. Instead of just checking if a player is grounded, we'll check whether the player is grounded or if this timer is below a certain threshold. Once the jump has happened, we'll need to set this timer up to a high value. This stops the player from continually jumping in the air. The final and most complicated feature we'll implement applies to both planar and vertical movement. At the start of the video, I mentioned that the physics system stops us from moving into a wall. Well, this is a double-edged sword. Suppose we're moving near a wall and our velocity has even a slight velocity into that wall. Well, the physics system is going to stop our position change no matter what. Instead, we'll need to use the collide and slide algorithm. I actually discovered this algorithm through stumbling on someone else's video. If you're interested in implementing this algorithm, I would recommend checking their video as well, as it's a very in-depth explanation. I would also read the research papers that are included with that as well. In short, when we're about to apply our velocity, we want to pre-check if that vector goes into a collider. If that collider's dot product is of a certain sliding angle threshold, we apply a slide. Now, why do we use the dot product here? The dot product tells us how two vectors are directed towards each other. The dot product multiplies each component of a vector and sums up their product. By normalizing both vectors, each vector is going to be of magnitude 1. Now if two vectors are facing each other, then their value is going to be 1, because 1 times 1 is 1, and all of the other components zero out. If two vectors are opposite of each other, the result is -1 for the same reason. And finally, if our vectors are perpendicular, the result is going to be 0. We know that one of our vectors is our velocity vector, but where do we get our other vector? When we do our capsule cast, the collisions hit variable will yield a normalized normal vector. By the way, the word normal is used way too much in mathematics. Anyways, the normal vector is which way the collision's face is facing. Back to our collide and slide algorithm, we check the negative of our threshold to decide whether or not to apply our algorithm. But what exactly does this algorithm do with our velocity vector? Well, it removes the velocity going into the wall so the physics system doesn't stop our position change. We can also do this algorithm recursively if that result also causes us to slide into another wall. To wrap up this algorithm, I also check whether or not our controller is in the air. If we are, we just zero out any planar movement and stop any further extension. That way, the controller just falls to the ground. Finally, this concludes the first pass of our character controller. While I'm unsure of the exact project requirements right now, this controller gets us through a lot of our basic needs. And as a nice bonus, the character has a lot of niceties towards game feel. While these features aren't important for a minimum viable product, you can argue that these fun features help with personal motivation to keep working on the project.
Plus, I'm just in pre-development right now, so the project management side, that's mainly out the window for right now. So if you're interested in more of these videos on just exploring random topics in game development, please consider subscribing. In the next episode, I'm going to be talking about camera controls. So until then, I hope you have a nice day, and I'll see you in the next one.